continuing our discussion of contingency tables, and what I want to show you in this segment is that the probability of any particular values in a contingency table depend not only on the numbers, but on the protocol that was used to gather the data. And this is a point that's very often missed in the literature. So let's consider three protocols. The first protocol we'll call Protocol 1. It's actually called in various fields either Retrospective Analysis, or more commonly it's called a case control study. And the idea here is that we decide what size samples we want of, for example, patients with a disease. We'll call that column C1, and we're going to go around to hospitals and round up a certain number of those patients so that this marginal, the number in C1, is going to be fixed. And then we'll have a control sample, so we'll decide that we need maybe the same number in a control sample, maybe a slightly smaller number. In any case, that will be column C0, and we'll find that many patients to participate in the study, that many individuals, and that number will be n.0 down here. Now what we're interested in is some factor, like were those patients vaccinated or not. Let's say that that's it. And we can't really control in the experiment, let's consider this column, the control sample, what fraction out there in the population either were vaccinated, let's call that probability Q, or were not vaccinated, probability 1 minus Q. So this probability Q is a nuisance variable. In other words, under the null hypothesis, both columns, the patients and the controls, should share the same probability of having previously been vaccinated, but we don't know what that probability is. Now what can we compute for the probability of finding exactly the values n00, n01, n10, n11 under the null hypothesis? Okay, let's start with this column. n0 is fixed, and under the null hypothesis we'll just have a random draw with probability Q of the n.0 to see how many happen to end up in this bin. So that's, it says bin, but that stands for binomial probability. It's the binomial probability, when the probability is Q for each individual event, of drawing n00 events out of n.0 tries. And then I've put a check mark in this box to show that there's no new probability here. Once we know the number in this bin, then because this marginal is fixed, we know the number here. But we still haven't determined what happens in the second column here, in column C1. Here, the marginal n.1 is fixed. The probability Q is fixed, even if we don't know what it is. And so we simply make n.1 draws with probability Q, and there's a certain binomial probability of getting the actual observed number, the n01 here. And then once again, once we know that, since we know the marginal, we know the value here. So the probability of this table under the null hypothesis is simply the product of these two independent binomial probabilities. I've written that out here, and here I've written out using the binomial probability formula what it is. And now we just have to stare at the algebra of this for a second. You can see we have some q's to some different powers, and we have some 1 minus q's to some different powers. And if we combine those powers, we get q to the n0 dot. Where did that 0 dot come from? Well, n00 plus n01 is the sum over all possibilities of the second index, and that's therefore the marginal n0 dot. And similarly, 1 minus q to the n1 dot. And then these binomial coefficients make this combination of things in front. But when you look at this, you say, I bet this is a piece of a binomial probability itself. And in fact, it is, because we can just pull out whichever factorials we need to turn these two terms into this binomial probability here. That's the binomial probability with probability Q of drawing out of all of the possible events in the table. That's this, exactly the number n0 dot. That would be the number, of course, in this row marginal corresponding to probability Q. And then the factorials that are left over turn out to be these. And lo and behold, this is exactly a hypergeometric probability distribution. That's why we reviewed the hypergeometric probability in the previous segment. So we can write the probability of this table as being a hypergeometric probability, and we can call that the probability of the table given the marginals. And then what we have in front of that, this binomial probability, we can call that the probability of this particular marginal, for example, that's this row marginal up here, given the nuisance parameter Q. And the probability of the table really does depend on this nuisance parameter. You could do numerical examples and take extreme cases of different nuisance parameters given the data seen, and you'd find that you would get different values of the probability of the table. Here, just to remind you, is the little picture that goes with this hypergeometric probability from the previous segment. Now let's consider a different protocol, protocol 2. This is called a prospective experiment or a longitudinal study. Here the idea is we identify in advance samples for these factors, maybe a whole bunch of people who have been vaccinated and a whole bunch of people who have not been vaccinated, and we enroll them in our study so that their number is fixed. Notice now it's the row marginals that are fixed. And then we follow them over time. That's why it's called a longitudinal study, and see over maybe the next 10 years how many get the disease and how many don't get the disease. Now the nuisance parameter here occurs over the columns. In the whole population, we don't really know what fraction of population is going to get the disease, and only by assuming a value, p, for that parameter, are we able to actually compute the probability of the table. So the logic is very similar to before, but the actual table has been turned on its side, as it were. So now we start with the idea that in this row we know how many events there are, n0 dot, and under the null hypothesis, with probability p, we just draw from that number n0 dot to figure out the probability of getting exactly what we observe, the n00 there. And once we have that, then this follows by just subtracting this cell from the marginal. Similarly, we get this binomial for the probability of this cell, and this cell then gets fixed by the fixed marginal. So the probability of the table now, this is the same arithmetic as before, so I've left out a couple of the steps, is a hypergeometric probability. It's the same one as before for protocol 1. It's the probability of the table if the marginals are fixed. But now this is something a little bit different, because this is a binomial probability depending on the nuisance parameter p, and giving the probability of having seen a particular column marginal n dot 0, which you see is the one down here. Protocol number 3 is called a cross-sectional or a snapshot study, and that's a study with no fixed marginals. So an example is we're going to test all the residents of Austin for both whether they have a particular disease and what their factors are. We have two nuisance parameters, p and q, because we don't know a priori what fraction of the population should either be in one row or the other, or should either be in one column or the other. Now if we assume values for those nuisance variables, then under the null hypothesis, the probability of being, say, in this cell is p times q, and the probability of being in this or this cell is 1 minus p times q or 1 minus q times p, respectively. And finally, this cell, we see it's going to be a probability for each event of 1 minus p times 1 minus q. So the question of, given those four probabilities, what's the probability of seeing this exact number of events? That's exactly the question that's answered by the multinomial distribution. And so the probability of the table, I've here just written out the multinomial distribution. Now, surprise, if you play around with this and try to pull out that hypergeometric probability that was common to protocols 1 and 2, you can do it. And you get the hypergeometric probability, the same one that we saw before, and we're calling that the probability of the table given the marginals. And now it's multiplied by two binomial probabilities, one which is the probability of seeing a marginal given the value of the nuisance parameter p, the other given the probability of seeing a different marginal given the value of the nuisance parameter q. Now, why didn't we have to know any of this when we did that first example using a chi-square test on a contingency table? We had a contingency table that had large numbers of counts. And asymptotic methods like chi-square typically are equivalent to estimating these nuisance parameters p and q from the data given. And it's pretty obvious how to do that. For example, if we want to know the value of p associated with this row, we can just look at its row marginal, n0 dot, and divide that by the total number of events, n dot dot, and that's an asymptotic estimate of what the value of p is. And similarly in the columns, from the column marginals and the total number of events, we can estimate a point maximum likelihood estimate of the value of q. So in effect, that's how people proceed. But when the number of counts is small, that maximum likelihood estimate of the nuisance parameters p and or q may be the maximum likelihood estimate, but the true value of p or q might be quite different. Is this beginning to sound a little bit Bayesian to you, a little bit like something that we've encountered in an earlier segment? It should, actually. We met this back when we were talking about the town family, and we were trying to estimate a parameter, and we first started out estimating it. You're supposed to be able to just remember this tiny little picture here. We estimated it as its maximum likelihood value, but we saw that the right thing to do was actually to estimate its whole distribution and then integrate over that. And that was our example of what was called an empirical Bayes method. So that's where we're actually heading here. We're heading from classical frequentist perspective on contingency tables and towards a more Bayesian perspective. But we have to finish with the classical frequentist perspective before we can do that in a later segment. So in all three cases, we got a product of nuisance probabilities which depend on the unknown p and q. And then we got this factor that was the same under all protocols. And when that happens, it's something called a sufficient statistic by frequentists. I have to admit, I'm never quite sure how to know whether a statistic is sufficient or not, but here's the textbook definition down here. A statistic is sufficient when no other statistic, which can be calculated from the same sample, provides any additional information as to the value of the parameter. And I guess that applies here, although don't quiz me too closely on how. Now, what many people do with contingency tables is use something called Fisher's exact test. Fisher's exact test ignores the nuisance probabilities p and q. It just throws them away, and it uses the hypergeometric probability that was common to all three protocols and says that's the probability of the table, And now we're going to use it in our p-value tail test, as I'm going to come to quite soon. You can also view this probability as the probability of the table when all the marginals are fixed, both the column marginals and the row marginals. Let's see how that works. Well, in this 2 by 2 case, if you're going to fix all the marginals, then there's only one degree of freedom. We could do that by a calculation of 4 cells minus 4 marginals, adding back in the one duplicated marginal, namely the sum of the either column or row marginals. But in any case, there's one degree of freedom. And we can call that N00, and just to have an easier letter for it, let's call it K. And you can see then that the probability determined by K is this combination of things. Let's reason through. We know how many total events we have, so let's figure how many ways we can pick n.0 of those events and put them into somewhere into this column. Well, that's n dot dot choose n.0. Okay, we have the events in that column. Now let's figure out how many ways we can put exactly k of them into this cell. Well, that's n.0 choose k. Well, what remains? What remains is just to figure out how many ways. We know now how many events are in this column because it's the marginal determined from the total in this one. So the only remaining question is, in this marginal, in this column, how many do we put into this cell? And that's n.1 choose n0 dot minus k. Why minus k? Because although there were n0 dot events in this row, we already assigned k of them here, and therefore it has to be drawn from the other ones. So that's the numerator, the number of contingency tables that have all of the same fixed marginals as our data. Now we want the probability of seeing the value k, so we have to normalize this by dividing by the sum of the numerator over all possible values of k. Well, this first term doesn't even depend on k, so I can pull it out, and then I'm going to cancel it, and then I have a sum over k of these terms that are up here in the numerator. So I've written that here, except I've made one additional step. This sum is a well-known sum of binomial coefficients, and it's called Vandermonde's Identity. And Vandermonde's Identity here, I've written it out here, and you'll see that it allows me to replace the sum over these two things with the sum of the numerators in a single choose function up here, and the sum of the denominators here, giving n0 dot here. I'm not even going to prove Vandermonde's identity for you in any formal way, but I can prove it for you in words. How many ways can you choose a subcommittee of size R from a committee that already has n Democrats and m Republicans? Well, obviously on the left-hand side, it's the total number of candidates choose R. But on the right-hand side, you could divide it up as, first let's ask what the possibility is for each value of the number of Democrats. So for each value of k, it's the number of ways we can choose k Democrats out of n. And then to fill out the rest of the committee, it's the number of ways you can choose r minus k Republicans out of m. And obviously if you add these up, you have to get this. Is there a protocol for where all the marginals are fixed? Is there an actual way to gather data that way in an experiment? That's kind of interesting, because if there is, then the Fisher exact test really is exact. You've gathered the data in a way that all the marginals are fixed. It's hard to think of, but the answer is yes, there are some examples where Fisher's exact test would be, as the name says, exact. So here's an example. Suppose the United States Senate, there are 100 senators, forms a baseball team. A baseball team always has 9 players. Now the question is, Did the Democrats, who are in the majority, use their undue influence to get more Democrats on the baseball team than Republicans? And here's the data. There are 60 Democrats in the Senate in this example and 40 Republicans, and there are always 9 members on a baseball team. And the way it came out is there are 7 Democrats and 2 Republicans. The other things here just follow by subtracting from the marginals. So if you think about this, you'll see that all the marginals were fixed in advance before we saw the data. We knew the number on the team, we knew the total number of senators, and in particular we knew the number of Republicans and Democrat senators. So there are examples where the Fisher exact test is exact, but they're few and far between. Now all of that in this segment was about the distribution of tables under the null hypothesis. So quickly now we have to go through the rest of the paradigm for making a tail test. What do? We have to pick a statistic. A statistic for this table, a common statistic in use, is called the Wold Statistic. The Wold Statistic is computed as follows. Let's start down in this line. First, we're going to compute a probability. We're going to estimate, I should say, the row probability. And we do that by adding m in n and dividing by the total of capital M plus capital N. So that's just a variable we're going to call p hat. Then we do the corresponding row probabilities separately for each column. In other words, m over capital M and n over capital N. And those are P1 and P2. Now, under the null hypothesis, P1 and P2 should be estimating the same probability as P hat, because under the null hypothesis there's no association between the rows and the columns. So the Wold statistic is just constructed to be the difference between those estimates, and then it's divided by something that, if you work it out, I'll leave that as an exercise, is an estimate of the variance of this difference. In other words, the square root is the standard deviation of this difference. And the whole point of constructing it this way, using the p hat and using the total column marginals m and n, is so that this asymptotically becomes a true t-value drawn from a Gaussian distribution if m and n are both sufficiently large. Okay, that's just background, because you'll remember you're allowed to make up any statistic you want if it seems to be a good statistic for detecting a deviation from the null hypothesis. And what really matters here is the P1 minus P2. Let's also note that the value of this statistic, t, when all the marginals are fixed, is monotonic in m, the number that occur in this cell here. Why is that? Because the p hat isn't going to depend on m, because if we increase m, then we'll have to decrease n. And as you increase m, p1 increases here, and p2 decreases because n must decrease, and therefore the difference is monotonic. We'll use this fact in just a second. Now, I'm introducing the Wold statistic because that's just a very commonly used statistic. You could have used the Pearson chi-square statistic that we defined in an earlier segment. You can use the Pearson chi-square statistic even when the number of counts is small. It's a perfectly good statistic. What you can't use is the assumption that it's chi-square distributed, and that's why you would be using the Pearson chi-square statistic, but in Fisher's exact test. So here's what Fisher's exact test looks like. Let's do a numerical example. Is this table a significant result? Let's see. Well, in this column there are 24 events, and about a third of them were in the first row. And in this column there are 29 events, almost 30, and only 3, so only about 10% were in the first row. So is the fact that we got only 10% in this column and more like 33% in this column, is that statistically significant or not? So what do? We compute the numerical value of the statistic, say the Wold statistic, for the exact data that we have. We now loop over all possible contingency tables that have the same marginals, both row and column. And you'll see in this case there's just one free parameter, 1 degree of freedom. We've put it here before and called it M, because if we know this, then we know that this cell must be 11 minus M, because 8 plus 3 is 11 up here. And we know, looking in this column, that this must be 24 minus M. And if you work it out, this one must therefore be 18 plus M. And M can vary from 0, which would make this cell 0 and this cell 11, to 11, which would make this cell 11 and this cell 0. So we compute the statistic for each of these tables, for each value of M. And those are going to be the tables that are in the population distribution of the null hypothesis. But they don't come in with equal weight. The whole point of our previous calculations of the hypergeometric probability was about how to calculate what the weight is, what the probability of seeing a particular value of M here combinatorially is, and that was the hypergeometric probability that, if you go back and see how it was constructed, you'll see comes out in this example exactly this. Now we know where our statistic falls in the distribution of the statistic values from these tables, suitably weighted, and we can output the p-value, the tail test, to see whether our actual data is unlikely to be drawn from the null hypothesis. Now actually here in this 2 by 2 case, which is a trivial case, but a case that occurs often in practice, all statistics that are monotonic in M here are just equivalent for a one-tailed test. And the reason is, after all, we're going to take the different values of M, and they're either going to be to the left of what we observe, 8, or to the right of what we observe, 8. In other words, are they less than 8, equal to 8, or more than 8? And as long as the statistics are monotonic, notice the choice of statistic didn't come into this hypergeometrical weight, and so we'll have the same ultimate weight to the left of what we observe and to the right of what we observe, and we'll get the same tail probability. And let's now see how that works out numerically. So here's Fisher's exact test for our table. I'm going to define the probability function to be this hypergeometric probability, which now depends only on M, because I've put in these constants that came out of that particular table with 8 and 3 and 11 and so on. And I'm going to want to evaluate this hypergeometric probability on the integers from 0 to 11. So here, using array function, evaluate this function on this vector. And here I've printed out the vector of integers from 0 to 11 and the vector of probabilities that come out. And you see they peak somewhere around, let's see, 0, 1, 2, 3, 4, 5 they seem to peak at. I'm about to show you a plot of this, so don't worry. And now our event, which was in bin 9, that's because it had a number 8, but MATLAB indices start with 1. Okay, our probability has 0.03 because it's this bin right up here. And here I've summed what the total probability is to the left of the bin that we're in and to the right of the bin that we're in. And the p-value is the probability of seeing data as or more extreme than the real data. So it's the sum of these two. That is to say, the sum from bins 9 through 12, and it's about 4%. So if we were doing a 5% significance test, it would be statistically significant. So here's a picture of it. This is the histogram of those hypergeometric probabilities, and we observed the value 8, and so it's in this bin, and we would have to add this area to area 9, and then you can't even see areas 10 and 11 on this picture to get the one-tail p-value for that contingency table. If that contingency table was about vaccinations and disease, then probably the one-tail p-value is the one you want, because you're not really entertaining the hypothesis that the vaccination causes disease. You're entertaining the hypothesis that the vaccination prevents disease, and you want to see with what significance level you can prove that by a p-value test. If you were in a situation where you needed a two-tailed p-value test, then you have to add in some bins on this side. And now you start seeing why, in my opinion, Fisher's exact test isn't really as exact as people say. How many of these bins do you add? What does it mean to be as extreme or more extreme than 8 when you're looking for tails on this side? Well, you might say that you want to add just 3 bins that are more extreme on this side, so I'll add the first 3 bins, as I've showed here with this brace on this side. Or you might want to say that you should include this 4th bin because it said as extreme or more extreme, and you'll see that makes a huge difference, because in this numerical example, that 4th bin in a two-tail test has a lot of probability in it. So there are these little ambiguities lurking that we're going to come back to. So here's my editorial. We're going to learn an efficient way to compute Fisher's exact test, not just for 2x2 probability contingency tables, but for any contingency tables. And that's what people really do. But despite these words, Fisher, which is true, it was invented by Fisher, and exact, which is already questionable, as I've sort of indicated here, and I'll say more about later, this test, in my opinion, is simply not conceptually well grounded because of those P's and Q's. Virtually never are all the marginals in an experiment actually held fixed, so that neither protocols 1, 2, or 3 are being tested by Fisher's exact test. The best thing you can say about Fisher's exact test is that it's an approximation that ignores the nuisance parameters P and or Q in favor of a sufficient statistic, and that asymptotically, if the number of counts is large, this doesn't matter very much. So I just don't understand why people use the Fisher exact test. I think this is a historical accident, and I think that it's due to what we would now view as an outdated, frequentist worship of sufficient statistics, which I think is fishy.